Yeah, okay. Welcome to everybody. And before I start, I thank the organizers for giving me this opportunity to talk here. And really, it's a lot of familiar faces to see after a long COVID. So I'm very happy, and things are normal now. So what I'll be talking today is non-existence of motility-induced phase separation in one dimension. So you've seen from the previous talk that the existence of phases and their stability and whether there is a transition between them is a tough question, and kind of people have been with simulations it's very, very difficult sometimes to answer such questions, and any exact result is always helpful. So here I will be in one dimension. I will just give some kind of exact results. Okay, so phase separation, all it occurs in or coexistence, or they occur in all kind of scales, and like vinegar, oil vinegar, or you have seen it many times. So coexistence of states is there. So generally, the preliminary things are, at least the phases are well understood. It's like a two-phase versus one-phase scenario. And a very simple example, this is kind of an undergraduate lab. You can do this, like, you can take cyclohexane and aniline, you mix it, and around 40°C, that's kind of mix up and on a bottle. So, and this mixture is transparent. So if you put a ledger to the one and just a paper here, you see this kind of flashes. And after, when it cools down, suddenly this one disappears because this thing the phase separated state is opaque, okay? Because one of the liquid is opaque. So you can see this. So question is that can you see phase separation in one dimension? One dimension, because one dimension is simple and you can do some theoretical behavior, and you can study some theoretical behavior. So the answer is yes, and there are interesting systems under non-equilibrium conditions which exhibit phase separation transition in one dimension. So one specific example, just for demonstration, I just give it here, is that extended Kaas-Lebois phone model, which is like there are plus minus spins, there are particles which are plus or minus, they carry plus minus spins, and there is an interaction between the particles which is like Ising, okay? But the plus particle moves to the right with rate alpha, and minus particle moves to the left with rate alpha. So along with this, there is this Ising interaction. Plus minus can only go to minus plus. So plus also moves forward, and this delta V is Ising like. Okay. So if you look at this, that the density of plus and minus particle, both particles are separately conserved. Okay. So this has been studied in this reference, Mukammal, Khafri, and yeah, he's here, and many people earlier. And this shows a phase separation transition. So we'll show it here. So first, let us discuss the equal density case. Density of pluses is same as density of minuses, and let us consider that there is no interaction. So in the previous example, this epsilon equal to 0. Okay. So then the rate this becomes 1. And this model is just plus minus goes to minus plus, and along with this thing. Okay, so it turns out that there is an exact steady state. One can calculate it using matrix product answers, and there is no phase separation transition occurs in this system. That is known. But surprisingly, that earlier before we know this exact solution, numerical simulations earlier exhibited jammed and inhomogeneous states. Okay, so there are a lot of work in this. This model actually exhibit phase separation transition. Okay, so it turns out that these phase separated states are only long transients, and there is no phase separation in the system. Okay. So now let us go for interacting systems. If you have an interaction and you take any arbitrary density basically the ratio of pluses versus minuses is eta, pluses versus total number of particles is eta. And there is a very nice description of these models, like there is a very nice mapping of this model, which could give you some idea about this. The exact solution is still not there, but this is kind of quite accurate, the coarse grain description. So what you do is that you have a lattice, and in the lattice there are these plus and minus particles, and they move. Okay, so if you are just watching this lattice, particles are just moving. So there is a current which is flowing through the system. Okay. So what you can do, the vacancies, you can think that the vacancy is like a box, and the particles are the particles here. So this is the vacancy, it's carrying 1, 2, 3, 4 before the next vacancy. So box carrying 4 particles. And there is a vacancy here, 2 particles, the box carrying 2 particles. This box has no particle here, and this box has 3 particles. That's the meaning. And the rate at which particle transfer, that is same as the current which is flowing through a block of size k. Okay? If there are n particles, the size of the block is k. So this mapping is very nice, and this actually gives you a phase diagram in epsilon, which is the interaction, and eta with the ratio of densities. So here for low densities, sorry, low interaction and any density, you don't have a phase separation transition. You don't have an inhomogeneous state, and here you have a phase separated state. Okay. So basically, what we learn is that no phase separation without interaction. So epsilon equal to 0 means no phase separation. Other thing we learn is that the phase separated state, you always have a phase separated state if the interaction is very strong. Okay. So for any density, if you go very high, then you always have a phase separation. So these are the 2 things which you know. Okay. So now we'll go to motility, just to define the problem. What is motility? So motility are called motile particles, motile or active particles. So, if you look at biological systems like sperms or E. coli, so they have flagellas. Okay, so flagellas, through the movement of the flagella, the things push off. So basically, these are systems which are out of equilibrium. They consume energy to push through. And there are many biological examples here, and also there are artificial swimmers which you can produce, like Janus rods or Janus particles, like particles which are half carbon coated, which will act to laser differently. Or you have chiral particles like this, or you have vesicles. So there are many examples of motile particles, and they can change their direction continuously, like these particles will change their direction continuously, or they can change their direction intermittently. For example, if it is an E. coli, so it is moving, but then the flagellas are not instantly, the flagella cannot orient in the other direction. So basically it goes and then goes in the same direction for some time, and then suddenly change the start here. It goes in the same direction and suddenly change the direction, goes like that. And so intermittently change the direction. This is called run and tumble particles. So these are 2 different kinds of particles we have. So now what will happen if you take a collection of particles? So if you have collection of motile particles, it seems they phase separate. Okay, so that is the claim that is seen experimentally in many situations. So you can see their phase separated state, and question is that what you see with a short time, are they stable, right? Or is it that what we saw previously, that these are unstable, and it is only short time you see them as a stable particle. So this is the questions which we'll be asking, but not in 2 dimensions, rather in 1 dimension. Okay, so this phase separate, and this phase separation occurs not because of interactions, because of motility. Okay, so there is no interaction except the hardcore particle interaction. There is no interaction between them, and it is only the motility which induces this kind of phase transition. So it's just a collection of bacteria just produce this. So this is motility induced phase separation, MIPS. And what yes, if you want to, yes. So motility induced, this what I am talking is that motility induced phase separation, and what I'm going to talk today is that motility phase induced phase separation in 1 dimension. So if the 2-dimensional structure, if you take a slice like that, so this will have a kind of inhomogeneous state. Like if you plot density versus, the things are missing, density versus x, this is the x. So then you have this inhomogeneous density profile. That's what you expect if there is a phase separated state in 1 dimension. So now let us see that what we know about this. So this is one of the paper in 2008. So this is start take of run and tumble particles. By the way, in 1 dimension, just because you have 2 directions, left or right, you have only run and tumble particles. So plus can become minus. Okay, so you don't have continuous change of direction. It's not possible. Okay, so what they do is that they take a continuum density and without any noise, and write a Fokker-Planck equation, and then what they find is that this hydrodynamic description or mean field description actually gives your phase separated state. Okay, so like if you start with a density like that in certain parameter range, and if you wait sufficiently long time, you can get an inhomogeneous density profile as you have seen earlier. So this was stated like, I'm putting it here, self-propelled particles undergoing run and tumble dynamics leads to domain formation by self-trapping. Okay, so this is kind of a phase separation which has been known earlier, and there are several other works. This is just one example. There are several other works, mostly in, I'm talking of only one dimension, hydrodynamic, wind field, and simulations also exhibit apparent thing in 1D. Okay, so the passive particles do not phase separate in absence of interaction that we have seen, right? And at absence, of course, attractive interaction. So what we see is that active particles do phase separate, it looks like. Okay, so this was a little suspicious for me, and I thought that maybe one can study this problem a little better, and if you can get some exact solution. So what I want to study is the lattice model of run and tumble particles. Run and tumble particles because means that particle has two directions. So when the direction is plus right, like that, it will move this way. When the direction is left, it will go this way. The same particle, depending on, it can change its direction also. So let us say that you have a one-dimensional system with particles, some red particles which moves right and blue particles which moves left. That is the only system dynamics. Okay. If you wait sufficiently long, they will just, I will take a question later. So if you wait sufficiently long, then they will just kind of collide and make a jam state, right? I mean, this is the absorbing or jam state they will provide. There is no surprise here, right? Because one goes here and one goes right, and they will come together, and there is nothing, the dynamics will not allow anything, they jam. So question is that how to clear the jam, okay? So clearing of jamming can be done in a passive way or an active way. So let us see that what is a passive way, which we discussed earlier. You just exchange the particles, saying that whenever they come like that, but you say that you take this way and take this way. So if you do this, then the jam is cleared. And this model is called AHR model. And we know that there is no phase separation there. Okay. So now let us do it in an active way. Okay. What is the meaning of active way? Active way is basically the particles themselves can change their directions. So plus can become minus with some rate, and minus can also become plus with some rate. Okay. So then if you have a situation like that, jam situation like that, if this becomes minus, for example, this become minus, this can now move. Okay, so the jam can be cleared. Okay, so basically in this situation, if you take omega, the clipping rate is very high. Of course, there will be no jam. It's a homogeneous state, right? If you have a very, then their plus and minus are indistinguishable. So no jam for large omega. This is also studied recently by mean field theory, Rajesh and Dandekar, who are Rahul is here. Okay. So the question is that what will happen to this situation for small omega? So what I'm asking more specific is that you take dynamics A, which is here, and dynamics B, which is here together, and take small omega and try to answer what will happen in this situation. So question is that any small omega, will the jam clear or will it stay? That's the question. May I ask what you're asking?
Actually, I had a question was about the active particles. So if the active particles can change their like they can become from positive to negative. So like at what condition they can do this, the thing?
There is a rate omega. Maybe we could discuss it at the end. Okay. There is a rate omega at which it will do that. You know what is rates, right?
Yes.
Yeah. Okay. So with some rate they will flip.
Okay. Thank you, sir.
Wait, right? Yeah. So what I do is that okay. Okay. Oh, sorry. I missed it a little bit. Sorry. Okay, the jam is clear, and the question is just that for small omega, whether this dynamics will have a phase separated state. Okay, so then there is an exact solution for two RTPs for this model. Okay, so many RTPs are not solvable, but if you take just two RTP particles, just two particles, then this is the same dynamics. And what you have is that in these situations, there are two particles, so both of them can move right, both of them can move left, or they move like that, or they move like this. And because of the symmetry, you can say that this plus plus, when both of them are moving right, the distance between them, what are the probability? That should be same as this, because left and right is only your convenience. Okay? So similarly, this is the symmetry. and you can get what exactly people, there are so two probabilities, P plus plus n and P plus minus n, which means that there is a blue particle and there is a red particle and the distance is n. What is the probability? That's what you look for. And what we find is that they differ, and there is a discontinuity here of this one. So which means that there is a effective attractive interaction between the particles, the active particles. So this was not said explicitly, but I mean, so probably the reason for having a phase separation is this effective attractive interaction which is being created by two particles, and this is the exact solution. So now many RTPs in one dimension. If you take many such particles, there is no exact result. Okay? So we could not find it yet. So it's not, the solution is not available. So what we do is that this particular dynamics is same as three dynamics, like plus 0 going to minus 0, plus plus, because this is plus going to minus, but I'm just writing next side is 0 plus or minus. Okay, so this is same as these three dynamics. And what I do is that I just delete one of the dynamics. It is just for the solvability purpose, but this will not harm my proposition. Because what is happening is that so this flipping is just destroying the jammed state, right? So if you delete one of them, the flip will not occur. So if MIPS existed earlier, then just by doing this, MIPS will not disappear. It will occur more. Okay. So basically, this doesn't because change of direction is detrimental to the stability of MIPS. So deleting one rate is not harmful. So I take a model which is a very general model, like plus goes to like this, plus minus, and minus goes to this. But this is general thing which I want, general model which I want to write, but MIPS has a particular symmetry. You see, plus particle goes right, minus particle goes to left, but if you exchange the particles, right, I mean, red and blue, if you exchange, red becomes blue and right becomes left, so this becomes this and this is this. So the dynamics remain invariant, okay? So this is the symmetry. Okay? So which means that if you implement the same symmetry, although this is general, for RTPs, you have P minus equal to Q plus and P plus equal to Q minus. That is the thing which has to be obeyed. Okay, that is also studied by Professor Bomma and things like that. I forgot to put the reference here. Yeah, okay. So there are two parameters here. So for run parameters, plus P minus this, of them there are two conditions. There are two parameters. One is this velocity, P minus minus Q minus, and one is gamma, which is the asymmetry. Okay, P plus by P minus. Okay, so and you can see that when gamma equal to 1, which means that P plus equal to P minus, and with this condition, everything is just equilibrium, and there is all configurations are equally likely in this situation. So this is a very trivial case. So what I do now is that we use a mapping, which is exact mapping of this model to the R model. So any configuration of the system is just like that. No? There is a particle, and these are two vacancies. There is a minus particle, plus particle. This is a configuration. So what I do is that the plus particle is like a box, plus box. Okay, and there are two zeros are like two particles. Minus particle, minus box with one minus box, no particle. Plus box with three particles. Minus box with one particle, plus box with one particle. That's the mapping I do. So now the particle movement here, like with P plus and Q minus, that can be mapped like this particle going to right with Q minus. Q minus is the spin of the arrival block. So the particle goes to right, which depends on the spin of the arrival block, and goes to the left with spin, which depends on the spin of the departure box. Okay, I call them beads, and I call these are particles and these are beads, just to make a distinction in while I'm talking. Okay, so these are beads and these are particles and these are arms. Okay, so the arm dynamics, which means that plus can become minus. So the way I have defined is that this is just empty boxes or empty arms can change its color. Okay, so that is the dynamics. So that becomes little simpler to solve. Okay, so how I solve it is that there is a matrix product answer. So for next 2-3 transparencies, if you write, this is a solution method I'm describing in maybe 2 minutes. And if you don't go through this, it is okay if you have not done it earlier. But just let me tell you the idea itself. So basically, right, I'll summarize it. So for the rest of the one, I'll summarize it. This is for people who have already done matrix product transfer. So what you do is a plus particle with two particles, you write it a matrix called X plus with index 2. It's a matrix function. Minus particle with 0, which means that X minus 0, X plus 3. So you have some matrices. And you probability of this in the steady state is given by trace of these matrices, matrix strings. Okay, so that's the answer. You don't know what are these matrices. Okay, so the matrices x sigma k mk is the kth arm having sign sigma k and mk beats. Okay, so this is something we develop this kind of matrix product. It's developed earlier for hardcore particles. This is developed by us later. Okay, so then this is the procedure. I'm just saying that if you don't, so how to get the matrices? I just tell you the procedure, narrate it a little bit. So if you have a, this is the probability distribution. This is just a string of matrices product, and there is a trace, and this is just the particle conservation. Okay, and you have a master equations. You put in the master equation this equal to 0, and this will give you some conditions. Like if try to know some, so you have some kind of cancellation scheme, which is basically means that you need a reduction. So you have a metric string, so a string of matrices, you reduce two of, so here there is a cancellation scheme where three of the product of three matrices are reduced to two auxiliaries and one matrix. So this is a two-step reduction process with a scalar which is associated with this, H sigma sigma prime, which is a scalar. And I find that H sigma sigma prime should depend on Mn. Okay, so H sigma sigma prime, they're like, plus minus and minus plus, they're same, and everywhere it is 0. Red are all 0. Okay, but when they're same, plus minus, then this value is q sigma into 1 minus sigma prime. On the boundary, it is 0. So this is the trouble which I could not manage. Okay, so if there is no color mismatch, then it is okay. Either you make it red, then it is okay, or you make them green, that is also okay. So this is the problem. Okay, but this issue this is not an issue when q sigma equal to 0, because when q sigma equal to 0, then this becomes red, or gamma equal to 1, this becomes red. But q sigma equal to 0 means all particles move to the right. It's good, but useless, because it's just right. It's just asset in a ring. Okay, because so there are only, so other thing is that if there are only two RTPs, again, which means in our model there are two ones, this model is exactly solvable, because our cancellation scheme requires product of three matrices, reduce it to kind of two auxiliaries. So that is not relevant here. So for two arms, we have exact solutions. So for two arms, we have exact solution, and you can write these matrices are 2 by 2 matrices, and we can write an exact solution. Okay, so now what? So because, we took it to the ARN model, which could not be solved. The actual model cannot be solved and only solved for two particles. So now what? So what I follow rest is there are two routes. Okay, so you're here, and one route is the coarse-grained ARN model. Okay, so what I do is I take the ARN model and coarse-grain it. Okay, and other thing is that forcibly use this as an approximate matrix product. What I do is that this red ones, I'll make it green. Okay, so red ones make it green. So there's not exact solution because some of the boundary conditions are, mismatched. So, if I use this in both ways, I reach the same conclusion, no MIPS. But I'm sure you will not be convinced by this because this is not exact and ad hoc. I'm using something, only support is a numerical support. So I'll take you through a longer route. Okay, so a coarse-grained description of this model. Okay, so how do you coarse-grain now? Is that, so now there are two different kind of boxes, right? I mean, you have boxes which are two different colors, right? Red, green, okay? And what is happening is that particles are moving through this. So what you want to know is that just look at the beads and how many beads are moving through the system. So that will give you the local current. So locally, there is a current, okay? So you integrate out the spin degrees of freedom, that is called coarse graining, and you write it as if the boxes has no colors. And these particles now move with a rate which is same as the local current, okay? Which is the coarse graining. So now in the coarse graining, in the original model, you know that the particles, the jump of particles, they don't depend on the number of particles. They just depend on the sign of the neighboring box. So now in this coarse graining, you naturally expect that it will depend on generally it will depend on the number of particles, and it will depend also on the neighboring box, particle in the neighboring box also. Okay, so basically JMN is same as UMN. That's what we want to do. That's a coarse-grained description of the model. And JMN, how do you calculate JMN so that the model can be well defined? JMN can be calculated exactly because for two particles we know the solution. So we have a two particle, and for two particle we have a solution. This is, and you can calculate with probabilities you have calculated, you calculate a current, and the current comes out to be the current comes out to be very complicated. Like this, it depends M1 and M2 separately. But if you put RTP conditions, current just becomes function of M1 plus M2. So the current UMN becomes UM plus N. That's simple. Okay. So this process where the particles jump to the neighboring box depends on the rate of particle jumping to the neighboring box depends on both number of particles of the arrival and departure site is called Misanthrop process. Okay. And the Misanthrop process are not generally solvable, is not solvable for all rates, but this particular condition, like when the rate depends on the sum of the number of particles of neighboring boxes, then it is solvable. Okay. And the solution is given by this. And along with the solutions, we have now two constraints. The total number of particles is M, and N plus M equal to L. That's our system. Okay. So then you have correspondingly you have two fugacities, Y, which corresponds to M, which is the number of beats, same as the number of vacancies. And Z is that. And what you do in a thermodynamic limit, you can eliminate Z using a thermodynamic limit equation in the thermodynamic limit, and you can write rho Y, which is 1 minus Y. Okay, so that's the density in this situation, how it depends on a fugacity called Y. So now what do I gain here? It's just this. So let us see that what is the phase separation criterion for phase separation. Okay, so I'll just discuss it very simply. Probably many of you know, but this is very simple in the sense that if the system phase separates for some rho greater than rho C, okay, rho greater than rho C, the system phase separate, which means that you have these two phase and it's a coexistence phase and a single phase. So you are going like that. So here it is a single phase, and up to rho C, it is in a single phase. And if you go here, you have coexistence. Okay, so rho greater than rho C, you have a coexistence. If this happens, then up to this, it remains homogeneous, of course. And a homogeneous system has a good description in my grand canonical ensemble. It's a grand canonical and canonical equivalence holds. So if you study a system in grand canonical ensemble, and you demand that phase separation occurs if the maximum achievable density in a grand canonical ensemble is less than the rho C, equal to 1. Okay, so if the maximum achievable density in a grand canonical ensemble is less than 1, then you have a phase separation. That is because you cannot, by tuning fugacity, if rho C is less than 1, let us say 0.3, then you cannot tune your density to get any density above 0.3. Okay, so this equivalence breaks down, and there is a phase separation transition occurs. So in our case, rho Y equal to 1 minus Y. So Y equal to 0 is the maximum density. Y is the number of vacancies. Okay, so that means there is no phase separation in the system. Okay, so how good is the coarse grain description? You can calculate this current, but you can also calculate this current numerically. And if you take asymptotic form of the current is that. So in asymptotic form, J is same as UM. So UM inverse is a linear function of M inverse. So this is the this equation actually is this, with a slope this and intercept this. So if I calculate this from numerical simulation, I should expect a straight line with a y-intercept 1 minus gamma, like 0.6, 1.6 here, and here, and this is the slope. So for very large omega, actually they are matching. But if you go, this is a large omega, this is small omega. For small omega, there's still a straight line, but the values, the asymptotic value is same, but the intercepts are not. Intercept is same, but the slopes are little different. Okay. Okay, so what I do next is that you calculate the marginals. What is the distributions of particles in different boxes? Okay, the marginals is just exponential distribution, and you know that a distribution when it is exponential, it just cannot support any phase separate coexisting state. So again, there is no coexistence state, but PM can be calculated from numeric simulations, and it is supposed to be exponential, which means a straight line, which is a straight line here, but the values are not matching very well, particularly for small density and small omega. Okay, that is the case, but we don't need all the details. Just having exponential is good enough to say that there is no phase separation transition, and we have good confidence why it is exponential function. Okay, then I go to the other route. Okay, because this route is other route is shorter. So I just, what we do is that you replace this by it's a 6-minute route. So approximate matrix product state. And what we have is that approximate matrix product. So this is what, and which means that you extend the same matrix solution to many RTPs. What you have exact for 2, you extend it to many particle system. It's the same thing. And we get rho y equal to this, and rho star, which is at y equal to 0, again it is 1. So no MIPS. Okay, just this much probably we would not have believed. So how good is this matrix product solution? And well, this is kind of very good. Just to calculate that, we calculate 2 quantities, which is the average number of beats per plus arm. So number of beats in arm divided by number of plus arms, because plus how many number of plus arms, that is also changing with this, in the situations. So this is also as a function of this, as a function of y, and you can, and y as a density, you know, so you can replace it. So the fraction of arms having internal degree plus, how many among the arms, how many are plus? That is also another quantity you can calculate. These are simple quantities. And if you want to match for different densities for the matrix product answers, these quantities match very, very well, I think. Okay. So although I'm calling it as approximate matrix product answers, it's kind of quite good. Okay. So in summary, what I want to say is that these models, like what I discussed, is a restricted run and tumble model that doesn't have MIPS. And what I say that any other model with liberal tumbling dynamics, because this is restricted, any liberal tumbling dynamics would not be any help. So this model doesn't have, the actual model doesn't have MIPS. So there is no MIPS. Okay. So one question might occur is that how can one possibly generate a true MIPS phase in 1D, stable MIPS in 1D? Is it possible at all? So this is a speculation that, I'm just saying that, if you take a very slow omega, let us say omega goes as 1 by L. Okay, so then system size goes to infinity as if the flipping never occurs. So in these such situations, things can occur. So there is this work, very recent work where people take, the flip rate is 1 by L square, and the run rate is 1 by L, and they show that there is a phase separation transition. Or if you take bias, this thing, yeah. If you bias the thing also, it can happen. So this work is done with my student, PhD student, Indranil, who is here. And MS thesis student is Adarsh Raghu, who is now in King's College. He's doing his PhD. Thank you.
Abhishek, for this very interesting talk. So now, if there are any questions. Okay, let's first, Greg.
Yeah, so I'm not sure I understood in which sense it is approximate, and how control do you have on this approximation that you propose? I mean, this matrix, and that's. What's the motivation for that, and in which sense it is approximate? I mean, that means.
Yes. So the approximate in the sense that I have. Okay. So there is this auxiliary here. Okay. The auxiliary value of the auxiliary here is Q sigma times 1 minus gamma to the power sigma. That's the value of the auxiliary here. And the value of the auxiliary, the boundary is 0. Okay. So if I have a small Q sigma and small gamma, then this is of the order gamma square, 0 square. So and that limit, this and that, both of them can be set 0. So that will match. So I have a kind of X. That's the approximation.
Okay, so it's kind of small gamma expansion.
Small, yeah.
Can you improve on it systematically?
No, because you have to find matrices. Like the matrix, the dimension of representation of the matrices cannot be obtained just by kind of expanding or something. It should be different matrices altogether with different dimensions. So I just by doing 2-dimensional matrices will not work.
Okay, thank you.
Speculative question. I want to understand the whole thing, whether it has a quantum version, whatever you have discussed. My question is, suppose if there is a way to convert the particle from active to passive, and then the strength of activity, suppose I give it a name, a strength of activity is stronger than the interaction outside or smaller than the interaction outside, will there be a critical point in that case? So self-interaction is weaker than the external interaction or stronger than the... So in
Yeah,
that
no,
case.
I will not answer this. I think I cannot, right, here also, whether there is an actual critical point or not, that we could not settle very clearly. So
But did you study the, like this
No.
way I'm talking about?
quantum, no.
No. So, yeah.
So I have a question about, so in the matrix, okay, so you have two ways, Coscrane method, which does not seem to work for low omega, right? Does the matrix product method work for low omega?
Yeah,
And
better.
so in our paper, we had results for low omega also,
Mhm.
where one result we had, for example, was that the number of particles in a single cluster
Yeah.
grows like 1 by square root omega.
Yes, I think it's a good one, right? Probably
Can you check?
we'll discuss. We'll check. Yeah,
Okay.
let's check it. So yeah, we should check this with a small omega result which you have. I think this is better because this is the way omega goes. So you can see that here there is no, so this is, in this case, this is the small omega case. So the difference is whatever difference you see.
Quick question. So there are models of run-on-tumble particles which are not confined to move on a lattice, but move in the continuous space. We've studied some parts of that where you do see dynamical clustering, but never a true bulk phase segregation. The lattice results that you showed will carry forward to the case when the particles are not confined to move on a...
Yes, the other way to ask is that what happens, it's the same questions, I'm just revising in a different way, saying that, initially when I saw that 1D, what is that? I forgot, sorry. So there is a model by MIPS and group, the first paper which I talked about, which talks of continuum model, right? So you might ask the same question saying that why do I see in the discrete model there is no phase separation? Why do they see the kind of inhomogeneous state what they see, and what is the status of that inhomogeneous state? So I would say that these are long transient, it will disappear. So what goes wrong there? If you have a continuum one, it is not a problem. I think what goes wrong is that the noise is not properly handled, right? If you have integrate, when you write a density, you integrate, you don't see particles, you just see the densities. And when you write an equation, you don't take care of the noise as such, and you write some from the symmetry. And the noise, even if you want to you put ad hoc as a Gaussian noise or something. So it's, I think, the play is of the noise. So then here, once you state the dynamics, the noise is automatically handled like the way it is. I don't have a control on it.
Then maybe.
Yeah, okay.
So let's thank both the speakers of this session.